All right, let's take a look at friction. So friction, as we learned before, is a contact force that acts parallel to two surfaces and opposes their relative motion. So if you have two things touching and they're trying to move, there's going to be friction between them. Two factors are going to determine the magnitude of the friction. First is, we'll say, the roughness of the surfaces, and then secondly, how tightly the surfaces are pressed together. So if two surfaces are squeezed tightly together, friction will be higher. If they're rougher, friction will be higher. But the reason that we have friction is if you zoom in on a surface, what you'll actually see is it's, jaggedy with all these bumps and whatnot. And so if another surface is sitting on top, it might also be kind of, jaggedy. And then when you try to move them relative to one another, you can see that in this region here, they kind of have locked together in a way. And that means that when you try to move it, this side right here will bump into this piece and it'll get kind of caught. And, it'll be like if you're trying to push up against a wall. If you keep pushing, eventually it'll kind of bounce up and over, and then it kind of, bounces along the surface. And this is why, as we'll see later, you've got two kinds of friction. One where the objects are stationary relative to one another, and one where they've started to move relative to one another. So if we want to calculate friction, we have two kinds. We have static friction, and in this case, the force of friction will be less than or equal to mu s times Fn, and then kinetic friction will be equal to mu k times Fn. So let's add some labels here real quick. So static friction, that's this force. Kinetic friction, that's this force. The mu s right here is the coefficient of static friction. And the mu k right here is the coefficient of kinetic friction. And then Fn is the normal force for how tightly these two are forced together. So the mu, we said, is the coefficient of friction. And that will represent the roughness. And you've seen that we've got two. We've got one for the coefficient of static and two for the coefficient of kinetic. The only difference between these two is static is, as it sounds, when the two objects are stuck together, when they're not moving. And then kinetic, when they actually are moving relative to one another, that's where you're going to have kinetic friction. So that's what the two types that you have are. And then Fn is, as we said, the normal force. And that represents how tightly they're pushed together, and it will typically be proportional to gravitational force. Or in other words, the weight. So if something is heavier, something is more massive, it's going to be pulled to the ground harder. And that means it's going to be the surface between that object and the ground, those surfaces are squeezed together tighter. That's why we typically think that something that's heavier has more friction, because it does, because it's typically pulled tighter to the ground. You'll notice in here perhaps that we've got this less than or equal to. That's because with static friction, it always equals whatever force is trying to get the object to move until you overcome it, at which point you switch over to kinetic friction. So this is what you saw way back when in the introduction activity, where you increase the friction, you increase the push force on the box up until I believe it was 125 newtons. And that's where you saw the static friction get bigger and bigger and bigger and bigger. And then as soon as it started moving, you saw that it dropped. And so that's what happened, was we went from static friction to kinetic friction. Kinetic friction, or the coefficient of kinetic friction, is always going to be less than the coefficient of static friction. And this is because if you think back to that example that we gave of kind of the bits and pieces kind of locking together, once it gets moving, they haven't kind of settled into those grooves, they're kind of bouncing along the top. That means it will resist the motion less than if it was able to kind of lock into place. So let's take a look at a couple examples here. So the first example, how hard would you need to pull a 65 kilogram skier for them to move at a constant speed across the snow? And they gave you these coefficients of friction. So if we have our skier, they're being pulled by you, so we'll say F pull, and they're being slowed down by friction. What kind of friction? Well, they're moving, so it's going to be kinetic. And so if we want it to be a constant speed, that means we know that the net force equals ma equals 0 because there's no acceleration. So that means that Fp plus F friction equals 0. That means Fp equals negative F friction. And so if you're going to pull, we know that we want that to equal the friction, which is going to be the normal force, times the coefficient of kinetic friction, because we're moving. So Fp is equal to negative mg times mu k, because in this case, the normal force pushing up has to counteract the gravitational force pulling down, because the skier isn't sinking into the snow, they're not flying up into the air, they're just pulling along. So in other words, in this example, the horizontal forces have to be equal and opposite, the vertical forces have to be equal and opposite. So Fp equals negative of the force that's being pulled, but since that force is being in the negative direction, and we actually don't even care about direction because they're just asking how hard, which means magnitude. I'm just going to drop the negative here and go to, I'm just going to drop that from all of this and throw in absolute value signs. Right there. So the absolute value of those two has to be equal. Oops. So Fp is equal to 65 kilograms times 9.8 meters per second squared times the coefficient of kinetic friction of 0.1. Fp is going to be approximately 65 newtons. I'll let you go in and actually calculate that if you're curious, but it should be about 65 newtons because we have about 1/10 times about 10, so those should roughly cancel, so we're going to be left with just the 65-ish. For our second example, a box is sliding across the floor. It starts with a speed of 5 meters per second and then comes to a stop in 1.9 seconds. What is the coefficient of kinetic friction between the box and the floor if the box weighs 150 newtons? So we have our box with m equals 150 kilograms. It's got an initial velocity of 5 meters per second, and then eventually it comes to a stop. And delta t equals 1.9 seconds, and we have v equals 0 meters per second. Well, we know that as this is traveling, the only thing acting on it is force of friction. Then we've got force of gravity pulling it down, the normal force pushing it up. So those two have to be equal because the box is staying on the ground, right? It's not going up into the air or falling through the floor. So in other words, Fn equals Fg, or the magnitudes equal each other. And so we want to find the force of friction. Well, the Fn plus Fg will cancel out, so the force of friction is going to actually equal the total force, which will equal mass times the acceleration. We can find the acceleration from the information given to us here, so v minus v naught over delta t should equal a. So in other words, force of friction equals mu k times Fn m times v minus v naught over delta t. So mu k equals m divided by mg, because I'm going to put in Fn equals Fg, times v minus v naught over delta t. And mu k is equal to 1 over g times v minus v naught over delta t. And then I'll leave that for sake of time. If you want to go in and calculate that, you can. But otherwise, if this tracked and made sense, that's great, and you can move on.